Hi everyone. Now I am going to explain about image segmentation using thresholding techniques from Unit 3. Coming to image segmentation. So segmentation is the process of dividing an image into multiple regions or boundaries or backgrounds so that they will be a meaningful, and each region would be the pixel or pixels with similar properties, like the properties can be a color, texture, or any intensity, and it separates the objects from the background and essentially the first step in computer vision pipelines. So coming to the image segmentation, why it matters means it is broadly used in many fields like medical imaging and auto sensing and remote sensing and autonomous vehicles and robotics as well. So without segmentation, a computer just sees a grid of numbers with it sees the object. Coming to the thresholding is nothing but uh, a kind of segmentation. The core idea for the thresholding is a pixel is classified as an object or background based upon its intensity value. So coming to the steps, we should convert the image into a grayscale. First RGB format to grayscale format and choose the threshold value T, and this T should be anything. We get the T value from usually from trail and error method, and we should compare each pixel to T value and threshold value, and later we should assign back black or white accordingly based upon the binary rule. If our given pixel value is greater than or equal to our threshold value, we will assign a white pixel to it, which means 255. And if it is less than threshold value, we will assign a black. And after assigning, we will get the result in a binary format, binary segmented image format. So the analogy behind this thresholding is like setting a brightness cutoff on a photo. Anything above is light or anything below that is a dark. Coming to the bimodal histogram. Yeah. Coming to the bimodal histogram, we have here two phases, background and foreground. For example, let's say an image. The image will be divided into two parts, background and foreground. So here the images frequency intensity values based upon their frequency is plotted in a as a histogram. And the x-axis will be intensity level 0 to 255, and the y-axis will be the frequencies. So the histogram shows the frequency of pixel intensity values from ranging 0 to 255. The bimodal histogram has two distinct peaks. One is for background and another one is for foreground. So the value between these peaks is ideal threshold location. We will get a threshold here with the dotted as red line. T is placed at the dip separating the two peaks at the middle point. And coming to multimodal histogram, it occurs when it exceeds more than two phases are required. So the basic rule for this multimodal histogram is for n pixels there should be n-1 threshold, and pixel values in range is tk to tk plus 1 for region k plus 1. For example, let's say there are two bimodal histogram. If for one model, for one phase it will be from 0 to k, and for next model, for next mode it will be from k plus 1 to 255. Like, it will be separated like that. So coming to multimodal histogram, it occurs when the image contains multiple distant objects or regions. So each object has different intensity values separating each peak in that. Coming to its applications in multimodal histogram, we use it in MRI brain scan, and if we say in brain scan, there is a gray matter, white matter, and also cerebral fluid. So there are more than two objects here. So in this case, we use the multimodal histogram, and also single threshold T is not good enough for classification regions, which means coming to single threshold T, which is global thresholding. There are multiple thresholding that we will discuss later. Single thresholding has multiple limitations. So it will underfit the image in some cases as it misclassifies the regions. And coming to the solutions, we use the multiple thresholds like T1, T2, T3 instead of single threshold by following the another thresholding techniques. In each interval between thresholds maps to one region class. And the effect of noise in thresholding and effect of illumination in thresholding are some few important topics. Coming to the effect of noise, so basically in thresholding there are two major noises that are as a limitations. One is Gaussian noise and another one is salt and pepper noise. We have to remove the noise in beforehand to before performing the thresholding technique. So by using the median filter, we can remove the salt and pepper noise, and by using the Gaussian blur technique, we can remove the Gaussian noise. After that, removing the noise, we can perform the thresholding technique to get the accurate peak peaks and threshold values. If we perform the thresholding without cleaning the image, without removing the noise, then it's chooses the wrong threshold value. It leads to incorrect object or background classification. So basically, let's understand what noise actually is. Noise is something that is unwanted random pixel variations added to the image. So if the noise stays in the image, the value between the peaks fills up and the threshold becomes unclear. So if we choose the wrong threshold, it leads to incorrect object classification. So salt and pepper noise is damages the thresholding value, and also Gaussian noise smooths the peaks, making them harder to find the threshold value. So in median filter, we know we will find the median of the pixels and we'll replace it with median pixel. And coming to Gaussian blur, we will take a kernel and we will it in Gaussian kernel it gives the more weightage to center pixel. We will after finding the kernel, we have to multiply the kernel with the image correspondingly. We have to move that kernel to the entire image, and we need to sum the products of each pixels and replace it with that value. This is about the effect of noise in thresholding. And coming to the effect of illumination in thresholding, let's understand what illumination is first. Illumination is nothing but the effect of light on the object. So there is a real world example is shadows, spotlight effects, and reflections, sensor sensitivity variations. For example, let's say there is a text on paper under the light, So it some letters are darker and some letters are washed out because of the illumination effect. So for this, it leads to the uneven lighting causes different regions of the same object to have different intensities. So if we have a single global threshold value that fails one part of the object is correctly classified, and it is unsure about the other object, whether it is classified as correctly or not. So for this, the solution is adaptive or local thresholding. So how adaptive local thresholding differs from the global thresholding means it computes the different thresholds based upon the neighbors pixels intensity values on each subregion. And alternative for this solution is we can also perform the background normalization. In that the model and subtract the illumination gradient first. Then we can also perform like this as well. So in coming to adaptive thresholding, it computes a local threshold for each pixel neighborhood, and it is also robust. Coming to basic thresholding, basic global thresholding algorithm. First, the steps are like this. First, we need to convert RBC to grayscale image, and then we need to select the initial threshold starting with t is equal to 128, which is mean of 0 and 1 to 55. You can take any threshold by following the trial and error method, and then segment the image based upon the threshold. If it is greater than threshold, assign it to the one part. If it is less than one threshold, assign to the other part, and compute the mean of the both groups, mu1 and mu2, and update the threshold based upon the mean of both mean intensities, and then repeat this process until you get the convergence. Typically, the convergence takes place in 3 to 5 iterations. It well works for bimodal images mostly. Coming to Otsu method in automatic threshold selection. So we in this method, which is better than both global thresholding and adaptive thresholding. It will instead of manually assigning the thresholds, it automatically finds the threshold in this one, and also faster. Here, what we are trying to do is to maximize the interclass variance, which is given by the formula mu square b equal to omega 1 omega 2 into mu 1 minus mu 2. Here omega is nothing but the probability of that class, and mu1 is nothing but mean of that class. Uh, so coming to the steps in Otsu method is first we need to compute the histogram and then normalize the histogram and try to find all possible thresholds like for class 1 and class 2. So SN0 to T for class 1 and T to T plus 1 to 255 for class 2. Segregate it as a background and foreground for two classes and compute the probabilities for two classes, omega 1 and omega 2, then the mean of two classes, mu 1 and mu 2, then compute the inter-class variance, which is given between in the slide, variance formula. Try to maximize it, select the optimal threshold. Yeah, it's about the method process. At the end of the algorithm, we will find the threshold that maximizes the variance between two classes. It scans all the possible thresholds and picks the one with the highest between the variance. So this method is gold standard for automatic global thresholding, uh, widely used in OpenCV and Matplotlib applications. These are the same as discussed as steps. And multispectral thresholding means instead of grayscale thresholding only uses one density channel. It loses color information. So if you use multispectral thresholding, it uses three channels like RGB simultaneously. Each pixel is represented with a vector that consists of RGB, and threshold becomes a region in 3D space. So objects with similar grayscale levels also with different colors can be classified in this, can be distinguished with this multispectral thresholding. It is widely used in remote sensing and medical fields. In remote sensing, we can segregate the vegetation, water, and urban areas by using these three channels, red, green, and blue. Coming to the comparison between global Otsu method and multispectral, here basic global method is manual and iterative, and remaining two are automatic. Input is grayscale for all three thresholding methods. Histogram is not needed for basic global method and needed for both the Otsu method and multispectral method, and handles the noise. Coming to handling the noise, Otsu method is it handles better. And coming to the efficiency and fast, uh, all are almost same, but Otsu method is very fast with a big O of 256. It is mostly used for natural images and documents. And coming to real world applications, it is used in medical imaging, object detection, and remote sensing. Limitations, coming to limitations, it fails in histogram when histogram is not clear and very sensitive to image noise. So we have to remove the noise in beforehand, and also sensitive to uneven illumination, and also it cannot distinguish the objects with similar intensities, and also when it is limitation for when there is no spatial context, when it ignores the pixel neighborhood relationships. These are the following limitations. And coming to the advantages, computationally very fast and works excellent for bimodal and high contrast images, and it is easy to tune and foundation for more advanced segmentation methods. Yeah, these are key takeaways from this video are segmentation, thresholding, and multiple thresholding techniques. Thank you.